Hello, welcome to this reading session. Today I'm going to read this paper, Tabular Data Deep Learning is Not All You Need. So this is basically something I'm doing for myself. I don't generally read papers and like put them on YouTube and I mean, I would like to do it more professionally in the future. By professional, I mean with better setup and more planned videos maybe, but this is just for me. And yeah, if someone wants to watch this, uh, sure. But it's more towards like to basically improve my reading comprehension and also my understanding of research papers. Uh, I was definitely never a person who like read a lot of stuff. I ended up doing this kind of stuff because I like research and I like to keep up with the state of the art technologies in general. But most of my learning has been from, you know, most from YouTube and other, Coursera and stuff like that, resources like that. And then second would be classrooms and slides. I try to read textbooks generally speaking, but I've never been a huge reader throughout my life. But as I uh, probably tried like read a few papers, probably less than 50, between 50 to 100 maybe, but not uh, particularly, with the utmost dedication and comprehension. Uh, and usually it takes me like 10, 20 sittings to even read a full paper completely. So today this is a 13-page paper. It doesn't seem to be very complicated. I watched a video on it. So basically, I know about this paper because the author, I think, I don't remember who. It was a post I saw on LinkedIn, the two authors in this paper. But one of the authors, he posted on LinkedIn saying they have 1,000 citations on this paper. So congratulations to Ravid and Amit. Amit AI, Amit I. Uh, so sorry for butchering your names, but I believe these. I know that Ravid is from NYU. I remember seeing that this post. It was posted by someone from NYU, so it could be Ravid, but both could be from NYU. We don't know. Anyway, so I'm just going to read this without wasting a lot of time. Mm, right. So the title is Tabular Data. Deep learning is not all you need. Abstract. A key element in solving real-life data science problems is selecting the types of models to use. Tree ensemble models such as XGBoost are usually recommended for classification and regression purposes. Regression problems with tabular dataset. Kind of putting words into the paper, but yeah, let's try to be more accurate. However, several deep learning models of tabular data have been proposed, claiming to outperform XGBoost for some use cases. This paper explores whether these deep models uh, be a recommended option for tabular data by rigorously comparing the new deep models to XGBoost on various datasets. I see. So basically, they are trying to, uh, or they did compare some deep learning models to XGBoost on various data sets. We will look into that as we read the paper. And in addition to semantically comparing their performance, we consider the tuning and computation they require. Our study shows that XGBoost outperforms these deep models across the datasets, including the datasets used in the papers that propose the deep models. Okay, now that's a huge claim because if these deep learning models were published, and then they say, let's say, what they say, yeah, and they are claiming to outperform XGBoost for some use cases. Maybe they didn't properly do the hyperparameter tuning, patching, or whatever it is. But the authors here claim that they have used XGBoost, and it uh, is it often. It doesn't say like often or always, but yeah, outperforms these deep models across the datasets, including the datasets used in the papers that proposed the deep learning models. Right. We also demonstrate that XGBoost requires much less tuning. Interesting. Uh, I mean, my assumption was that deep learning, deep learning, the authors of these deep learning papers did not do a lot of tuning, but now they say they did much less tuning. Maybe these guys are really good, you know. On the positive side, we show that ensemble of uh, deep models and XGBoost performs better on these datasets than XGBoost alone. Yeah, so there's like a lot more to explore here than in general. There's a lot to explore here. Keywords, tabular data, deep learning neural networks, deep neural networks, tree-based models, hyperparameter optimization. Cool. Introduction. Deep neural networks have demonstrated great success across various domains, including images, audio, and text. Uh, these papers, I guess, Devlin and et al., he et al., Van Den Oud et al. There are several canonical architectures for encoding raw data into meaningful representations in these domains. Not sure what canonical means in this like context. According to or according to ordered by canon. I guess like typical architectures. Yeah, it's more like typical architectures. These canonical architectures usually perform well in real-world applications. In real-world applications, the most common data type is tabular data, comprising samples in rows with the same set of features columns. I'm assuming if someone is here or in general at this point, like reading this kind of paper, we know what tabular data is, right? So I'm just gonna like skim through this. Tabular data is used in practical applications in many fields, including medicine, finance, manufacturing, climate science, and many other applications that are uh, based on relation databases. Basically, SQL and stuff like that. During the last decade, traditional machine learning methods such as gradient boosting decision trees (GBDT), I don't uh, remember what like can't remember what gradient boosting or like XGBoost actually is. I know I studied that like a little bit during my machine learning courses that I've taken, but yeah, let's just like read about it quickly. Gradient based on boosting in a functional space where the target is pseudo residuals rather than the typical residuals used in traditional boosting. I have no clue what that means. Right. When a decision tree is weaker, yeah, it's like the next level of ensemble models. Yeah, it's kind of boosting is kind of ensemble learning method which trains the model sequentially, and each new model tries to correct the previous model. Okay, it combines several weak learners into strong learners. There are two most popular boosting algorithm, that is ADA boosting and gradient boosting. So here we talk about gradient boosting, and also let's just have uh, this. Let's go through this first. Oops. Yeah. As we know, ensemble learning helps in uh, machine learning result helps improve machine learning results by combining several models. So basically, ensemble learning is sort of like uh, taking a bunch of different machine learning models and it's like, yeah, kind of remember now it's bagging and boosting, but yeah, I don't remember. Like I kind of remember what ensemble learning is. So you take um, a lot of different models and take their average, or basically you take like a bunch of models and give weight to each model's result. So usually if it's like multi classification. So for each model, you kind of get like a softmax. So like probabilities of each model, of each class at the end, and then so that's if you're using multiple models, you have like multiple of sets of these uh, probabilities, and what you kind of do is you either average them and then do the classification, or you can do another thing, which is uh, give weights to each of these models outputs and then take uh, take the winner out of it. Anyway, so yeah, we're still here, right? Bagging and boosting are two types of ensemble learnings. There are these two decrease the variance of a single estimate as they combine several estimates, right? From different models. So the different model, so the result model may be with higher stability. Let's understand these two terms in a glimpse. Bagging, it is a homogeneous, weak learners model that learns from each other independently in parallel and combines them for determining the model average. Okay, uh, that's a bunch of jargon. So let's read this. Bagging, also called bootstrap aggregating, uh, or the other way around, is a machine learning ensemble meta algorithm designed to improve the stability and accuracy of machine learning algorithms used in statistical classification and regression, decreases the variance and helps avoid overfitting. It usually is applied to decision tree methods. Bagging is a special case of model averaging approach. So, description of techniques. Let's read through it quickly. Okay, tuples. Each iteration, I training data set di of the tuples. Uh, Sampling with the replacement method. Okay, not sure what that means. So, t tup selected via row sampling with the replacement method. Okay, then a classifier model mi is learned for each training set d less than I. Each mi classifier mi returns its class prediction. I've always hated Geeks for Geeks. I'm just gonna put it up there. Never was a fan of Geeks for Geeks, but yeah. Suppose a set of D tuples at each iteration I, a training set of DI tuples of DI of D tuples is selected. What is a sampling replacement method? So basically, if you pick something up, it's like you can basically. So every time you're sampling, you're not deleting those. Like you're gonna reuse all the get that. But then a classifier model MI is then a classifier model MI is learned for each training set D less than I don't know what that means. Nah, never like really understood things from uh your who data can like data cans. So what is bagging in machine learning? Guided with examples. This implement in Python. Okay. Ensemble methods are powerful techniques in many in machine learning that combine multiple models to improve overall prediction accuracy and model stability. Bootstrap aggregating, better known as bagging, stands out as a popular and widely implemented ensemble method. In this tutorial, we will uh, dive deeper into bagging, how it works, where it shines. We will compare it to any other ensemble method, boosting, and look at a bagging example in Python. By the end, you will have a solid understanding of bagging, including best practices. By the way, reason I'm looking so much uh, into uh, boosting or bagging, it's because we are using XGBoost in this paper, right? That's like the main algorithm that's being tested with other models. So it's only fair to actually understand what model they're using. So anyway, ensemble modeling is a technique that combines multiple methods to improve overall predictive performance. The basic idea is that a group of weak learners can come together to form one strong learner. An ensemble method typically consists of two steps. Multiple machine learning models are trained independently. Okay, their predictions are aggregated in some way, such as by voting, averaging, or weighting. I hope we learn what those are. This ensemble is then used to make the overall prediction, right? Ensembles tend to yield better results because the different models complement each other and overcome their individual weakness. Interesting. They also they all keep saying this. They also reduce variance and prevent overfitting. But why? But why? Some popular ensemble methods are bagging, boosting, and stacking. Stacking? Where'd that come from? Ensemble learning is used extensively across machine learning tasks like classification, regression, and clustering to enhance the accuracy and robustness. A lot of like words which I should know, but I just don't. Uh, yeah, I guess when the data distribution changes, we still need to have a model that is stable. So that's robust. But like, I don't understand how a model is actually like robust if the data source is changing. Uh, I mean, bagging because it's not like because we are doing because these models are actually learning from the same data set anyway. I understand accuracy or precision might increase, but uh, I would assume that robustness is more. a resultant of the data quality, or like the variance in the data itself instead of like the variance in the models. Anyway, in detail, each model is trained on a random subset of the data, on the sample data with replacement, meaning that the individual data points can be chosen more than once. Wow. I took like 10 minutes to explain that one sentence. Not really, but yeah. This random subset is all known as a bootstrap sample. By training models on different bootstraps, bagging reduces the variance of individual models. It also avoids overfitting by exposing the constituent models to different parts of the data set. Yeah, see, now that kind of makes sense. But robust, I don't know. I don't think so. That's just sounds right, but doesn't even sound right. The predictions from all the sampled models are then combined through a simple averaging to make the overall prediction. Okay. This way, the aggregated model incorporates, right. This is what is bagging, right? So, before we get to, I think we're already here. Uh, yeah, robust and accurate again. Oh, wait. Yeah, again, come on. Don't make that claim if you're not going to hold it. Also, like, do not believe the 50% off on data camp. It's always there. Second thing, do not pay $300 for. I know I paid. I'm just saying. There's always 50% out there. Just look at it. Just try to find them. Anyway, wow, this is an amazing image. It kind of gives us what boosting actually means. Before we go there, let's see actually if we have what is boosting somewhere. A guide to the gradient boosting algorithm. Learn the inner workings of gradient boosting in details without much mathematical headache on how to tune the hyperparameters of the algorithm. The body of this article is long but detailed, so we'll make the introduction as short as possible, directly starting with the question, why bother with gradient boosting? Good question, man. There are a number of excellent reasons. Gradient boosting is the best. I'm gonna skip that. Gradient boosting is highly versatile. Okay, gradient boosting is interpretable. I like that. Uh, Gradient boosting is well implemented. Good. Gradient boosting wins. I'm just gonna skip these. What will you learn in this tutorial? The most important takeaway of this article is that you leave with a very firm grasp of the inner workings of gradient boosting without much mathematical headache. After all, gradient boosting is for usage in practice and not for analyzing mathematically. What is gradient boosting in general? Boosting is a powerful ensemble technique in machine learning. Unlike traditional models that learn from data independently, boosting combines predictions of multiple weak learners to create a single, more accurate, strong learner. I just wrote a bunch of new terms, so let me explain each, starting with weak learners. Weak learners is a machine learning model uh, that is slightly better than a randomly guessing model. For example, let's say we are classifying mushrooms into edible and inedible. Bruh. If a random model is 40% accurate, a weak learner would be just about 50-60%. Boosting combines dozens of dozens or hundreds of these weak learners to build a strong learner with the potential of 95% accuracy on the same problem. The most popular weak learner is a decision tree chosen for their ability to work with at most almost any data set. Real world applications of gradient boosting has become such a dominant force in machine learning. Please don't go away a little bit. Yeah. Gradient boosting has become such a dominant force in machine learning that it has applications that now span various industries from predicting customer churn to detecting asteroids. Here is a glimpse of its success stories in Kaggle and real world use cases. I'm going to skip this. Uh, the gradient boosting algorithm, step by step guide. Input gradient boosting algorithms works for tabular data with set of X features and a target Y. Like another machine learning algorithm, like other machine learning algorithms, the aim is to learn enough from the training data set to unseen, generalize well to unseen data points. To understand the underlying process of gradient boosting, we will use a simple sales dataset for with 4 rows using three features: customer age, uh, using customer age, purchase category, and purchase weight, and we want to predict the purchase amount. Mm. You're gonna sell different things to different people for different amounts. That's something that's legal. Yeah. The loss function and gradient boosting. Imagine in machine learning, a loss function is a critical component that lets us quantify the difference between a model's predictions and the actual values. In a sense, it measures how a model is performing. Here is a breakdown of its role. Calculates the error, takes the predicted output of the model and compares it to the ground truth, right? Guides model training. Just what loss means in general, I guess. I think it's mixing up terms. For example, a loss function doesn't guide. Okay, it does guide model training, I guess. Sorry. I guess it's fair enough. Cross interview. The function measures the difference between the two probability distributions. So it is commonly used for classification tags where the targets have discrete categories. Uh, Basic cross entropy. Okay, Curtis Spikes. Let's see what you wrote. All of the applications we use today incorporate a form of machine learning to enhance or automate a business process, blah blah blah, understanding cross entropy. Claude Shannon, the mathematical theory of communication. Uh, this is a cool paper. It is 54 pages. I'm not gonna read it because you've seen me read, not even done with one paragraph of the original paper, and I'm already somewhere else. Anyway, if a coin were tossed, it would have two possible outcomes where the probability of the coin landing on heads or tails is half. Okay. H is the negative P. Okay, this is like the log likelihood, right? Just give me the formula, man. Wait, so we are looking at cross entropy, right? Yeah. Just seeing entropy versus cross entropy. That's known as multi-class cross entropy. Okay. So this is like, anyway. What if I use sigmoid with log likelihood of softmax with cross entropy? Is it fine? Because I see there's only little difference in the equation of cross entropy. Okay. The negative log likelihood, the equationality is also known as multi-class cross entropy. They are, in fact, two different interpretations of the same formula. The negative log likelihood of Bernoulli distribution, well, this is a Bernoulli distribution, multinomial distribution, multi-class. So yeah, this is like Bernoulli trails from our statistics class. Basically, yeah, you have Bernoulli's, you have binomial, and so on. For binary classification problems, softmax outputs two values. I guess in terms of negative log likelihood, we anyway. Let's not care about negative log likelihood. If someone wants to look into it, I think they should, and I'll probably look into it sometime soon when I come across it again. But yeah, but it's cross entropy is also known as log loss, a popular function used in machine learning to measure the performance of a classification model. It measures the average number of bits required to identify the an event from one probability distribution P using bits required, okay, using the optimal code for another probability distribution Q. This is the difference between the discord probability of a distribution A and the classification model and the predicted values. Okay. The same thing. This is GPT. Good thing, because I don't have ChatGPT up right now. Let me see what I can do. I guess I don't need to be logged in. Pretty sure it's gonna ask me to log in a while. Let's try to make the best of it. Uh, no one likes to just write properly. Reverse entropy function is used to find the optimal solution by adjusting the weights of machine learning model during training. The objective is to minimize the error between the actual and predicted outcomes, thus measure closer to zero is a sign of a good model. If you're familiar, what's the difference between cross? Okay, that's a fair question. Can we just call it the log loss, I guess? Hmm. I'm kind of thinking, like, if I remember how decision models work in the first place. It's complete classification tutorial. Information gain. Claude Shannon invented the concept of entropy, which means the impurity of the input set. In physics and mathematics, entropy is referred to the randomness or the impurity in a system. Information theory, it refers to the impurity of a group's examples. Oh, okay. I never thought of it like that. Information gain is the decrease in entropy. Gain computes the difference between entropy before the split and average entropy of the dataset based on the given attribute values. ID3, iterative dichotomizer. Decision tree is given the various information gain. This guy's making me mad. Iterative dichotomizer. Bro, 4D is the average amount of information to identify class label of a tuple in D. D is a data set. D, J by D, I access the weight of the jth partition. Okay, J is the partition, so you're like chunking it. And for A, D is the expected information required to classify a tuple from D based on the partition by A. Gain ratio. Information gain is based off the attribute with many outcomes. It means it prefers the attribute with a large number of distinct values. For instance, consider an attribute with a unique identifier such as consumer ID that has zero info because of peer partition. This max this maximizes information gain and creates useless partitioning. I don't understand it. Okay, let's read information gain again. Information gain is based for. Okay, wait, is information gain here? Magic. Anyway, Claude Shannon invented the concept of information entropy, which measures the impurity of the input set. In physics, it means something else. Information gain. Uh, Gain computes a difference between entropy before the split and the average entropy after the split. The data set based on given attribute values iterated dichotomy decision tree of algorithms is information gain. This is the same. article that told us to screw math. No, we don't hate this guy yet, okay? Let's not hate anybody. But we do not like some people. Anyway, uh, information again computes the difference between entropy before the split and average entropy after the split based on the given attribute values. Summation of the, yeah, probability of I into log 2 of probability, log base 2 of probability of I, where pi is probability that an, uh, okay, class ci. See like a example. Here. Okay, that's a lot. Information gained is the average amount of information needed to identify the class label, blah blah blah, blah blah blah, gain ratio. The attribute A with the highest information gain A, is chosen as as a splitting attribute. Nah, bro, we're not. We have better explanation. Hmm. The parent node into the weighted average of the entropies of the child nodes. Let's look at some PDFs. Yeah, very impure group. Cool. 16 by 30 of green circles, 40 by 30 of pink crosses. Uh, log base 2 of 36 of this probability is minus zero point 0.9 and log 2 is 0.1. Entropy is, and it just it does it. Uh, oh, so basically, okay, so if you have two classes, the maximum, uh, it could be either that like one, there are a lot fewer impurity, minimum or like less impure, or it could be very impure. And if it is very impure, then it's basically 50-50, right? So this 14 by 30 and 16 by 30 are basically close to 50-50. And entropy works in such a way that we would get one if the impurity is 50-50. Uh, Interesting. Two classes. What is the entropy of a group in which all the examples belong to the same class? Zero. Yeah, University of Washington. Cool, man. Information gain. We want to determine which attribute in a given set of training features, feature vectors is most useful for discriminating between the classes to be learned. Information gain tells us how important a given attribute of the feature vector is. We will use it to decide the ordering of attributes in the nodes of a decision tree. Okay. So entropy parent information gain is like basically entropy of parent minus entropy of child. What does that mean? So this is two classes, so I guess it's not that hard. Mm. So child entropy. So parent entropy is this thing we had before. It's 0.996. We just have two classes. Hmm. Why are we doing this? Okay, we split it in this way. Let's say you like split it in certain way. I think this is a little arbitrary. Arbit, 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 arbitrary.
Arbitrary. Arbitrary.
Arbitrary. Arbitrary. Arbitrary, like the split is arbitrary. Okay, when you're doing the normal entropy, like if you're just calculating it normally, uh, where is it? It's basically a sum, right? You're like technically taking those two sums and adding them. What node one, what feature should be used, what values, okay. Okay, so the classes are perfect, but basically it's two class, right? But basically, if you have multiple features, this kind of becomes harder. This kind of becomes more complicated. And the question is basically, how would you distinguish class one from class two, right? So split on attribute x. Ah, if x is zero, x is one, this is going to be one. X is zero, this is still gonna be two, but again, it's just one here. So we don't know, right? Uh, but seems like since this is again like zero and one, we're basically trying to find a breaking point. And since it's only zero and one, you kind of have to split on zero and one. And yeah, so here we still have two classes. So we would get certain entropy of 0.1984, 0.9184 and 0. And you take a weighted average. So this is like 3 by 4 into that, and this is 1 by 4 into the second one. And this is 50-50. So the entropy was 1 before, and the gain is 31.2. Interesting. Oh, and I guess you checked basically for Y and Z. Oh, right, yeah. Uh, for X, we had that weird situation where one of the labels was not uh, there yet. So here the information gain is 1 because if you notice it, it splits perfectly. Like if it's 1, it's 1. If it's 0, it's class 2. So it kind of splits perfectly. So I guess uh, like for that simple example, a tree of like size 2, like this is the parent node and this is basically the classification node is enough. And yeah, that's the end of this lecture. Great. So let's go back here. I guess see, in that example, beautiful example by University of Washington, we uh, had a very limited information of entropy, a limited explanation of what is entropy because of two reasons. One, we had only two classes. Two, the data points were binary, so it became very easy to split. But in reality, if it's so, it has to be some kind of quantitative data. We can't have like we can't have words or something. I mean, we can, but the basically how do we split it? If it's 0, 1, split it. But like if it's from 0 to 10, how do you split it? From 0 to 5 and 5 to 10. Uh, and if there are words, you could basically split them all in such a way that oh, these words going to this tree, and these words going to this the left tree or something like that. But if we can't do that, and we are generally like looking at complicated data and complicated classification, or I think even regression. I think decision tree regressor is also a thing we got to look into more. So I just noticed this thing. Uh, Attribute selection measures is basically the I kind of like skipped through that. I did not see it, but I think that's kind of important here. And information gain ratio, and gene index, I guess, are types of attribution selection measures. Mm, right. So it says the best source attribute will be selected as a splitting attribute. The best score attribute. Let's go to the source. Jesus Christ. There must be like one mistake somewhere. Is it some kind of injection? Yeah, this is the one, right? Construction. Yeah, semantic scholar. Can we see the paper? No paper link available. Yeah. Like try author. Let me just write to the author that that link is sending me to a slot machine or dating service. Yeah, I guess data camp is just being data camp. I can't find something, a place where like I can report something. No wonder they have mistakes on something. Seems like it's been read by a lot of people. These are like some very basic uh, concepts in machine learning. So I'm pretty sure a lot of people have read them, but I don't think they care. Anyway, So this is a paper that I found, which supposed to be the actual source, if I'm not wrong. Uh, yeah, which one was I reading? Yeah, the so-called source. That's the source everywhere. So yes, some of them are right. One of them, I think maybe the author himself owns that. Or maybe they own the domain and they just want some clicks. Anyway, please go away. Yeah, thank you. Heuristic for selecting the splitting criteria that best separates a given data partition D of a label class training tuples into individual assets. It determines how the tuples at a given node are to be split. The attribute selection measures provides a ranking for how each uh, tuples are tuples at a given node are to be split. The attribute selection method provides a ranking for each uh, attribute describing the given training tuples. The attribute having the best score for the measure is chosen, and the splitting attribute of the given tuples. Uh, this paper uh, perform. Oh my God. This paper perform gave comparative study of two attribute selection measures. The information gain is used to select the splitting attribute in each node in the tree. The attribute with the highest information gain is chosen as the splitting attribute for the current node. The Gini index shit, measures use binary split for each attribute. The attribute with the minimum Gini index is selected as the splitting attribute. The results indicating that predicting attribute selection with the Gini index is more effective and simple compared to information gain. I think I don't read these articles out loudly in general. I like read them carefully. Uh, so I never like see so many mistakes or this can be good. Data mining is the extraction of implicit, previously unknown, and potentially useful information from large databases. It uses machine learning, statistical, and visualization uh, techniques to discover and present knowledge in a form which is easily comprehensible to humans. Data mining functionalities are used to specify the kind of data patterns to be found in data mining tasks. Data mining, bro, I'm gonna skip this. Uh, Decision trees are powerful and popular tools for classification and prediction. Popular in English anyway. Decision trees represent rules which can be understood by humans and used in knowledge system such as database. Decision tree learning is a method commonly used in data mining. The goal is to create a model that predicts the value of a target variable based on several input variables. A decision tree is a flowchart-like tree structure where each internal node denotes a test on an attribute. Each branch represents an outcome of the test. And each leaf node, terminal node, holds a class label. The topmost node in a tree is the root node. A tree can be learned by splitting the source set into subsets based on an attribute value test. This process is repeated on each derived subset. in a recursive manner called recursive partitioning. The recursion is completed when the subset of a node has all the same value of the target variable. When splitting no longer adds value to the predictions in data mining, decision trees can be described as the combination of mathematical and computational techniques to aid the description, categorization, and the generalization of given data. I have no clue what that meant. It's basically jargon. The data mining is a combination of mathematical and computational techniques to aid the description, categorization, general. Please don't use sentences like that. The construction of decision tree classifier does not require any domain knowledge or parameter setting and therefore is appropriate for exploratory knowledge discovery. Damn, these data mining people love the sentence. Exploratory knowledge discovery. Wow. Yes. Decision trees can handle high dimension data. In general, uh, come on, man. In general, decision tree classifier has a good accuracy. Decision tree induction is a type inductive approach to learn knowledge on classification. The key requirements to do data mining with decision trees are attribute value description, object or case must be expressible in terms of a fixed collection of properties or attributes. Yeah, let's just go to the splitting. So-called splitting. Where is the splitting, man? Okay, just explain how decision tree works. Attribute selection measures. Yeah, yeah, information gain, gene index, and experimental result. Information gain, gene index, and basically they're talking about like these three: information gain, gene index, and what's the other one? Information gain, gene index. Thought there was one more: cross entropy, right? And information gain is basically entropy. Yeah. Okay. I think we use entropy in all of them. Let's see. Let's stitch this awful PDF. I don't want to be like too critical, but sure. And when people start watching my videos, I will be better. Uh, I'm really judging here. Iterative dichotomizer. Who named it? Iterative dichotomizer. Dan Ross. Did you do something? Iterative dichotomizer. Do you not like humanity? Thought this sounds cool, huh? Probably like, oh, iterative dichotomizer. I am so smart. Oh, where PI is. So let's look into this again. In 4D. Okay, so info-D here is basically the cross entropy. You know, this cross entropy we've been seeing in every other article. Yes. This, I think, this is softmax. This is not cross entropy. Just cross entropy. Yeah. Just why don't you just? Oh yeah, here cross entropy. Here, info D is cross entropy, and PI is the probability that an arbitrary tuple belongs and D belongs to class I. I think we already established that, right? So info AD is what J? Where J? What is J? The J partition. Yeah, it's basically that thing we used for like. Yeah, it's basically from the same thing. Instead of classes, we are doing ing. Jth partition. Are these like random partitions? J of 1 and V. Partitions random. Um, I don't know. Hmm, yeah, I need better. Let's not use. I mean, let's use have these here for now. To make sure we have the. But let's not use them. Please. Our business tree. School, please. Okay. Business tree. Ooh, 93. Try to talk optimizer. This uses gain ratios and cart is classified as a regression tree. Yeah, seems like a much better. I don't know. When I went from Geeks for Geeks to Data Camp, I thought that was beautiful. But now, just to understand, or I'm just dumb. That could be totally true. That's probably the best case, most important uh, factor. Oh my god, what is V, bro? They just use J instead of V instead of J, but due to the highest information gain will produce the plus split as long as it is doing as long as it's doing the best job at classifying the training data according to the target classification. The hell? Let's look for some PPTs. Ooh, are we cool enough for Caltech? I have no clue. I think I'm too down for Caltech. Let's try. Ooh, UPenn. I like UPenn. Yeah, here's another question, right? If it's like, why do you just have to? Okay, I guess the number of splits would be dependent on the number of different options you have for that uh, XYZ label. That's not label, or it's called the XYZ column data feature. Yeah, feature. Yeah, this is, I guess, what I was trying to understand. Decision tree boundary. What's the boundary calculator? Yeah, I get it. It's like the simple. Uh, it's cool, but how do we define the boundary? Let me get out of this stupid true false thing. Okay, what's the weight estimate greater than 60? Yeah, this is more okay. Occam's razor. Cool, bro, but just give me the basic understanding. Induction of decision trees. Best decision attribute for the next node. Cool. ID3. Yeah. Using an attribute, a good attribute splits the examples into subsets that are ideally all positive or all negative. Cool. Yeah, these guys took the slide from Washington. At least they gave the credit. If you don't understand here, I'm just gonna. If I don't understand here, I'm just gonna look for Tom Mitchell slides. Apex. Okay. Doing the same thing again and again. Okay. This formula. This formula again. And you. Yeah, I guess like that's for like the second or third split down the line. Just tell me, how did you decide to do the classification? Hmm. Oh, sorting. It's just sorting invariably. But then, what's S? This is just classes 9 positive and 5 negative. I'm gonna cry. I guess we could just take the median. That's probably one way. Is C D C I D C I S L. Hmm. Position boundaries still and what not in the context of numerical values directly influence. This you wanna tell me? Cool, it's a secret. Get it. SK Turn has probably some. code in binary that I cannot understand. Jesus Christ. No way. Okay. Maybe this has some answer to for you. Understood what bagging is. You have no information for me. I don't know what genie is anyway. It's basically 1 minus sum of probability square. So I guess like if we have like 50% of it, so that would be 0.5 squared, so 0.25 into 0.25. So genie impurity goes between 0.5 to 1, I guess. 0 to 0.5. Okay, because it's 1 minus, so yeah, that makes sense. Hmm. A guide to the gradient boosting algorithm. Let's just quickly try to understand what gradient boosting is and get back to the paper. I don't want to waste a lot of time on this now. I think you should like try to code a decision tree sometime. Hmm. Yeah, I should like note that down. Okay. Okay, we got a loss function which is half mean squared or cross entropy, make an initial prediction. It gradually increases accuracy. So to start the process, we need an initial guess of prediction. The initial guess is always the. So I guess when you're training instead of randomly training, are you basically using the same data every time for each model? The reason for choosing the average as to for the first round, our models predict that purchase are all the same. Initial guess of prediction, okay. Average of the target. Choosing the average as to with the chosen loss function and it is derivative. We are such a okay. Calculate the pseudo residuals. Okay. Build a weak learner. Next, we'll build a weak learner that predicts the residuals using three features. We have age, category, purchase weight. For this problem, we will limit the decision tree to just four leaves. Okay. Category is equal to E. Not sure what that means. Because that's just because we're using two four leaves. You're making this a classification problem. Okay. After the trees fit the data we make a prediction for each row in the data. Then we take the okay the average weight minus this predicted weight, so we get 123. A small error in the images which have been predicted purchase amount not predicted. Okay, got it. It's not like they can just replace the image. No, they have to put a note. Minus 32.55, which is exactly the same as observed value, $123.45. So building other trees right now, we are heavily overfitting our training data. We want our model to generalize, so to mitigate the problem, gradient boosting has a parameter called learning rate. So let's say ETA. No, why they call it ETA? Yeah, predicted cost. We made a small mistake, guys. We made a small mistake, which is 156 plus zero point 0.1 into this. So it's only 46. We now run through the tree and get 146 as a prediction. We continue this fashion. We get these new predictions. Taking the new pseudo residuals. We're taking the difference between these both, I'm assuming. Which is about right. So amount and new predictions. Okay. But that's just one. In practice, professionals often start with 100 trees, not just 10. Okay, we built 10 of these different trees. The only thing to remember is that we have to keep adding the residuals of each tree to the initial predictions to generate the next. For example, if we build 10 trees and the residuals of each tree are denoted as R, right? The next prediction will be P of 10 is 156 into the learning rate into the sum of all the residuals, where P10 denotes 10th round. To look into more, look into this like a better way. Yeah, I'm gonna stop this now and I'm going to like start it. by trying to get a better understanding of boosting. This is part one, I guess. Cool. Peace.